So I wanted to tell you, I mean, I don't know, because I promised, I think, in the abstract to link it to matrix models, but this is the kind of thing that somehow I feel myself not in the right form. First of all, I gave already in UK about, it talks about how
You have
to
to put the microphone on, I think.
Say it again?
Turn it on. You have to push the button and you should have a green light.
Yes, I have it. Yeah. Good. So, you're back. Good.
Sorry, yeah. I have to wait for it.
So let me erase something. And I don't know, so maybe to make a shorter story and ready to finish around 4. So what do you like more? Let me choose the thing on which I will focus. So multi-component Bazinization or matrix models?
Matrix models for me, I didn't hear the first one.
Sorry.
Multi-component Bazinization. Okay, matrix models. If it's matrix models, let us talk about matrix models. In matrix models, I understood just a little bit of that, so maybe then it will make my talk easier. But the thing that I understood was the following. So people want to consider different nice functions, So I'll make some statement, and so this statement of the following type. People want to have the function of the following type, so they take the integral over the space of matrices denoted Hn of C. I'll explain in a second what is the space of matrices. So here they have some special measure, and the measure I'll also explain in a second. And so they integrate exponent of -1 over gs, so gs is a genus parameter of some potential, which is a function, so it's trace of v of m. M is a matrix in this space of matrices, plus, and so it's a matrix model with one external field, Rm. R is an external field. So people look at this kind of functions. They want to look at this kind of things. And so in fact, so people take actually the limit for n to infinity, and they denote it by z. So it's a partition function that depends on what? That depends essentially on r, right? And nothing else. R, and we want to say that it's actually exponent of some sum over g from 0 to infinity, gs 2g minus 2 of some fg. So this is called partition function, this is free energy, this is external field on which everything depends. And so the space of matrices is just the space of all matrices that are can be conjugated by a Hermitian matrix to a diagonal one, where all the eigenvalues of this diagonal matrix lie on a particular contour C in C. So this is C, this is contour C, and we say that we take all matrices Hermitian conjugated to diagonal matrices with eigenvalues on C. C is fixed once and forever. V is also fixed once and forever. So these are the data of the matrix model. So the first statement that we have to understand that many nice functions can be written down in this way. Sure. So second statement is the following. So sometimes you want to compute something about this matrix model. For example, you can look at this Fg as functions of this R in a clever way. Of course, I mean you have to rearrange a bit this variables R. So you have infinite series of variables, right? R1, R2, R and capital, but then you continue because you take a limit. So it's a kind of, you consider symmetric functions in R's as your basic functions. The point is the following. So you want to compute something. For example, you want to compute derivatives of these free energies with respect to R's. Or in most cases, they talk about what they call correlation functions of the matrix model. And correlation function means that you insert here, so trace 1 over x1 minus m times trace 1 over x2 minus m, so on. So you can compute these things, and to compute these things is almost the same as to compute derivatives in R. So when you take derivative in R, it means that you put here m, and it means that you take the residue of this correlation function at infinity in x. So it's more or less, I mean, recomputable, at least for physicists at the level of computations. I mean, which is when I say like that, I mean it's higher than the one mathematicians can afford themselves. So it's recomputable. It's actually almost mathematical statements, in many cases mathematical statements. But the point is the following. So if you look a little bit at this integral a little bit, you can observe that it has an infinitesimal symmetry. This integral has an infinitesimal symmetry. I can change m by, so m plus 1 over, so actually I put here epsilon, meaning that it's infinitesimal, x minus m, so trace maybe. Or maybe like that, no, just like that, because then I'll take trace automatically, times y minus r. So if you think a little bit about this infinitesimal change of variables, and okay, I haven't yet said what's the measure. So the measure is a product of the natural measure I have on this contour, and so just z, and a hard measure on the space of Hermitian matrices. But the point is that this gadget, if you think a little bit, is infinitesimal symmetry of this integral. So you can write an equation what would mean that when you deform m with this with respect to this guy, the integral in the first order in epsilon doesn't change. You can write this equation. This equation is a non-trivial equation. And from that equation, if you look at it, and if you have some extra properties that I don't want to discuss now, but these properties are the properties of this type, that you have different kind of topological expansions for some auxiliary functions related to matrix model. You can say that, okay, so this equation that is called loop equation gives you a recipe how to compute correlation functions of your matrix model. And this recipe, so it was observed, I mean, by in different versions by Chekhov in R10, and is now known as in R10 recursion relation. And this is something that I want to discuss a little bit, and this is a place where we can see once again the same Givental group as we were talking about the first 1 hour plus epsilon. So what is an R10 recursion? I mean, it's kind of some formula, as I said. So this formula is very natural. If you start to derive it from in the way I just mentioned, so if you look at this infinitesimal symmetry, get this loop equation, look at expansions of different parts of this loop equation in GS, as formal series in GS, so you would get it. But let me now describe it. And description is like that. So we start. Let me describe a kind of simple version of that. Because in all examples that I used to study, I have only this simple version. You say that, no, well, maybe more complicated is okay. So you say that you have some curve, C. Just algebraic curve. It's called the spectral curve of the matrix model. You see the formula of this curve from the loop equation. So it's somehow related to the derivative of this V. So C is spectral curve. It's just complete algebraic curve, and in most cases, we think that it's C1.
There's nothing to do with the previous
one. Nothing to do with the previous one. Yes, sorry. So it was contour, and this is curve. It's very easy to observe the difference between contour and curve. So on this curve, we have two functions, x and y. They're kind of related to this x and y that we had there, but let us just say that now we give axioms. So now I give a kind of axiomatic description of what people compute instead of computing matrix model if they want to remain in the realm of mathematics. So x and y are some functions on this curve. C to C1. So meromorphic functions, maybe, or maybe even not meromorphic, but so there would be some restrictions on them. So also we want to have what is called Bergman differential, which is not a good notation, but we want to have a differential of the following type: differential B by differential on C times C with double pole on the diagonal and 0 A periods. But I mean, if we talk about CP1, as I said, so I aim to explain as simplest example as possible because it only gives us
What's after A?
and 0 AP rules.
Periods.
Yes, but I mean, say again?
What is an A period?
So you have to choose a basis, a symplectic basis in the homology of your curve. So half of them we call A, half of them B, and integrals over A cycles should be 0. But I mean, the point that for CP1, it's just if here is the coordinates Z and W, so we can just think that we have Z dW, Z minus W squared. So there is a unique gadget like that, and let us just use this gadget. So because as I said, so I don't want to present it in full generality. So then we want to reconstruct. So a recursion. So as I said, so it's biological recursion. Allows us to reconstruct some W. Okay, actually there will be G n's, but I mean we can remain in the in general 0 as I did in the first half of my lecture. And I want to show you what is the formula for this WGNs. So WGNs, first of all, what is going to be? It's going to be n differential on C times C, so in times. So like this. So and the reconstruction is the following. Like this D. So D is going to be just W02. So the reconstruction is the following. So maybe one question: do you prefer to see it for all general or just for general 0? It doesn't matter. It's just formally I talked only about general 0 so far. And now I kind of tend to talk about high general, but I can still talk about general 0. So the recursion relation is the following. So we can say that W 0, for example, let it be 0. Okay, so n plus 1, let it be 0. 0 n plus 1, depending on Z0, Z1, Zn is equal to. And before saying to what it is equal, let us talk a little bit about function x. So function x, we want to be a Morse function. And so when we have a critical point of this function, so it's x, critical point. This is my curve C, which is CP1. So if I have here some point z, I can always define locally z bar, which is just another point that locally near this point is projected the same under x.
Question, sorry. The W or the correlation function, right?
Yeah, they call them, now they're called correlation forms.
Oh, yeah.
Because they're really going to be differential forms and it's important. So they're going to coincide with the old correlation functions only in one particular choice of coordinate.
Okay.
So this choice of coordinate can also be part of the data. But I'll show you in examples how it works, because I'll give you two examples when I can get geometrically significant functions from some small input of that type. Good. So just what I want to say, that when we have a critical point of x near this critical point, we can split all the points in pairs, right? That projected the same. And also let me denote by P1, P, I don't know, for example, n capital, or maybe just, yeah, n capital is bad. PD, D is also bad. PR, we denote the critical points of each. And then they write the formula. It looks complicated, but in fact, if you think a little bit about that formula in terms of this loop equation, it's very natural. So that you have to take the sum, so I runs from 1 to R, of residue for Z, so approaching Pi, so this critical point, of the following gadget. So I write the formula and then we discuss it. So the integral from Z to Z bar of, I have my B, which is W02, so maybe I have to say 02 is B. So B, so I integrate with respect to the first variable, and the second is Z0, which is one more gadget that I have here. So divided by, I don't remember, there's some constant, maybe 2. Then I have here y of z minus y of z bar. If you remember, y is an extra function. And then I have here dx of z and times, so sum over all ways to split n into disjoint union of two sets, non-empty sets, I and j of w0 I plus 1 of z. So zi, when I say zi, I mean that I list here all the variables z with indices in I, times w0 j plus 1 z j.
Sorry, can you repeat? You removed, or what did you do when you write ZI?
Say again?
What did you say when you put ZI? What's
It's just that I want that I, so number of elements in I, so it's just all z's with indices in I.
Okay.
Right, so because it has to depend on, so the number of elements in I plus 1, cardinality of I plus 1 variables, and these variables are z and all z's with indices in I. And here z bar and all z with indices in j. I have this kind of recursion. So the claim is that this recursion replaces the computations with matrix models. Now, what we can do with this recursion? So with this recursion, we can say the following. So I'm thinking a little bit whether I can directly translate it to the language you would like, or I expect that you would like, because maybe you don't like the language you use. And
just one question: can we think about those guys as the alphas you have in the previous forum?
we are coming to that. So that's the theorem that I'm going to explain. So far we can't think like that, but we are approaching a moment when we can. So that's that's the point of that part of the talk. So that's actually, so I'm going to come back to high common algebras. But so you see, I mean, no, I would say, so our achievement is the observation that we have them there. So good. So, and by the way, so it's not only about genera 0, as I said, so we have it for all genera. Yes. So maybe let me first start with some nice examples, right? Nice examples are the following. No, I mean, how to say, whether these examples are nice depends on your background and whether you have ever heard about the gadgets I'm going to talk about. So one example is like that. So let us take CP1. So x is z plus 1 over z, y is log z, and okay, so when we have CP1, we have no choice for B02. So then what I claim is, okay, so that this W0n, when we consider it not as function of z, but when we consider is, okay, so maybe it's still I can write this 1zn, but now look, so z can also be considered as function of x, right? It's multivariate function, but still a function of x. We can take gradient at infinity, for example, and we can say that it's going to be sum of all possible d1, dn of the following gadget. So I put here tau d1 of omega, tau dn of omega, so cp1 times so dx1 dxn divided by x1, and I don't remember for sure, but maybe it's d1 plus 1 or something like that, xn dn plus 1. So this gadget, which is so a differential form on CP1 times CP1, so actually expands in this way. You have some coefficient which is easy to understand, and this gadget is a Gromov-Witten invariant of CP1. It's what is called stationary sector of Gromov-Witten theory of CP1. Namely, let me not explain it. So it's just important, for me it's only important to say that it's some geometrically significant number. Moreover, this geometrically significant number is related, as we can already guess, to these alphas that I had before, because Gromov-Witten theory is an example of high common algebra. So then, another example is the following. So let me maybe erase something, because if we, yeah, I can erase from the previous talk something. Another example is, for example, if we have still CP1, so x is equal to minus z plus all z, y is equal to z, and then we start the same procedure. So then what we get would be the following. It would be, so W0n is equal to the sum over all possible mu1, mu_n. So here I put something that I'm going to explain in a moment, 0, mu1, mu_n, and then I still put this dx1, maybe I have to put here some extra mu_i, I don't know, over x1. It's approximate formula because there is some very, very small combinatorial coefficient, like the protocol for mu_i's maybe, but I don't remember this coefficient by heart. Yes, maybe. In this case, it's going to be d exponent minus mu1 x1 d exponent. Oh, so now it's completely correct. Mu2 x2 d exponent minus mu_n xn. So now it's completely correct. Okay, so this gadget is just some factor. So it's clear that there should be more complicated function because of this logarithm. And this gadget is just Hurwitz number. So it's a number of ramified coverings of a sphere so that all critical values are fixed and simple, except for infinity, where you have ramification indices mu1, mu_n.
So you mean that you have computed your definition, which is up there, and you arrived at that?
Yes.
You're saying.
Yes. That's examples. I mean, I just wanted to stress that normally you should expect that you get some significant numbers, and these significant numbers are in some sense related to these Hypercommutative algebras. Because how this gadget is related to Hypercommutative algebra? For this gadget, we know the formula, which is called EDC formula, that it's equal up to some combinatorial coefficient times the integral over m0 n bar of 1 over 1 minus mu1 psi 1, 1 minus mu_n psi n. So you see there is some hidden, in this case trivial, but still some homological theory of the type that I have just erased when I have just a commutative product. But so you see that there is hidden again some link to the moduli space of curves we were talking about on the previous hour. Okay, good. So now we kind of should be convinced that we have a nice theory that produces significant functions, and now I can make a general statement about how it's related actually to Hypercommutative algebras. So the general statement looks like that. It's my theorem with Dunin-Barkovsky, Aranten, and Spitz.
And then just before you erase, the x and y, how are they encoded here? It's in the potential V, or?
It's in some sense this x and y of this. So if you look, I mean, you get this curve from the loop equation, and in this loop equation, this x and y are just these formal variables, right? So the loop equation somehow will relate to x and y. But it's not straightforward. I mean, when you look at this loop equation, you still have to do some extra steps to derive spectral curve. So I can't say it immediately how we derive it. Though it's easy, I mean, I can, well, as I said, so I have to define some auxiliary functions of this type of correlation functions in which I can derive equation of spectral curve. In terms, and this x and y would be exactly the gadgets related by this equation.
But you're saying that this functional equation
Yes.
doesn't depend on the, I mean, it's invariant under this rewriting you are saying. You said it's, the integral itself doesn't depend on this change of coordinates you were saying.
Yes.
So that's why it's strange.
But that's the point. They don't depend on the change of coordinates, but you would, if you would do it and naively expand, what does it mean? You get some equation, which you know that must be equal to 0 because it doesn't change it. And this equation is equation for correlation functions and some auxiliary functions. And when you expand this equation in GS, so what you get is a system of relations which is equivalent to the one I have on the blackboard for a particular spectral curve whose formula is then you see from that system of equations. So this works like that. So now relation to Hypercommutative. Hypercommutative. So it's let me write the names of my collaborators. Markovsky. Rantan and Spitz. So the story is like that. The story is like that. So we can always say the following. Yes, so maybe. So first of all, let me just generalize a little bit discussion, because you see what I need to know here, only the local expansions of y's near the point z, only the expansion of x near the point z, and expansion of my Bergman kernel near the point pi, right? I needed only local information, and in principle you can forget about the existence of a global curve, so you can generalize a little bit. But I mean, we can still talk when we have a global curve as well. So, but otherwise, we can say that we have just R germs of a curve, and we know expansions of Bergman kernel y and x near these germs.
Bergman kernel was this P differential?
Yes, yeah. It's a bad word for that, because Bergman kernel mathematics means something else. But unfortunately, classics of this science called it Bergman kernel from the very beginning. So now they try to call it Cauchy kernel or two-point differential. So they try to change terminology, but it's a kind of too late. Yes, because it exists only for too long time, for physics, for 5 years. For mathematics, it did nothing much. Okay, good. So the statement is the following. The statement is the following. That so let me. So you can always define. Some functions psi I depending on some auxiliary functions. So that and I mean the definition, as I said, the definition is straightforward in terms of this data. I just don't want to write down explicit formula, but in some sense it's not more a complicated formula than just expand or something like that. But it depends somehow on these local expansions. So I can write the formula in terms of Laplace transforms of these local expansions. But the point in the form, so then we can say that W0n is equal to sum over I1 IN D1 Dn now I have a kind of problem. So no, I'm a bit stupid because you will see what kind of problem I have. So let me put here 1 plus n, and here I put I0 and here I0. And now I want to say that what I have is so the integral over m0n, no 1 plus n, I'm sorry, of n of so psi 0 d0 psi n dn times, if you remember, I had this alphas, alpha 0, alpha n, it was just alpha n on the previous hour, and alpha n was some operation. And so some operation, and let me say that it was some operation on a vector space, right? And this vector space has some basis, ER. R is the same R as I have there. And also, so when I say this I0, so also we have some dual basis. So let's choose this kind of thing. Because now I want to take this alpha n, apply it to EI1, where I1 is this index tensor EIN, and then to apply EI0 star to that, because I want to have a number. I want to have a number. So times, so the product of, So differential of minus 2 d over d xi. Xi, I mean this I is just a kind of index to distinguish the copy of x. So k runs from 0 to n. Xk of this auxiliary function that I said it has just an explicit formula of so it is index I1 depending on xk. So this k is just to distinguish, and this is to the power dk. This k here is just to distinguish because we want to have for each input and output here a separate copy of x. If you remember, I want to have a differential form on c to the on cp1, maybe in this case I don't know, to the power k plus 1. So that's why. So this x are coordinates.
Why I1?
Ik. Thank you. Ik. So what I claim essentially, that there always exists in my previous terms. When I perform this operation, the claim is the following: there exists a high-com algebra on an R-dimensional model space where R is exactly the number of critical points, such that my differential forms that I get from another unintended topological recursion are represented in terms of this data. And another remark is that this data allows me to reconstruct the high-com algebra uniquely. So that's kind of, this data is equivalent to know the homology classes in general 0. In high general it's not true, but in this case at least, so I want to stress that I talk exactly about the same gadget as I was talking the whole previous hour. So I claim existence. Moreover, I claim the following. So this I have no time to explain, but I claim that I know how to identify this guy. And I can identify it in the following way. I can take a particular sum of R copies of one-dimensional high-com algebras. One-dimensional high-com algebra is almost nothing. And then, so this kind of local data that I have here, so this x and y, first of all, it tells me how I have to renormalize this local data of high-com algebra, right? Because there is some parameter. So when of course, this must be as an algebra, an idempotent algebra. So when I take the product of the unique basis element with itself, it's some constant times its basis element. And these constants are, roughly speaking, they are related to expansion of y near the critical points of x. So then, to this, if you remember, I was talking about the action of the Givental group. So I can represent this high-com algebra as a result of the action of particular element of the Givental group applied to this direct n sum of one-dimensional high-com algebras, where the element of Givental group is actually comes from the Laplace transform of my Bergman kernel, which is also part of my initial data. So I can identify all the ingredients of this guy to represent in the Givental way as Givental operator applied to a trivial high-com algebra. So the correspondence actually is in a constructive way. I can show how to construct all these alphas explicitly.
In the previous part, you were studying the stabilizers under the Givental group. So here, no, you're not looking at this kind of equation.
Yes. Moreover, so in this case, from what I said, it follows that the hypercommutative algebras that I can get are semi-simple all the time, right?
Yes, when we come to the element thing, if you have a semi-simple, then he knows all the orbits. Yeah, he was able to describe the orbits.
Yes. So it's in the same realm. No. I don't have to use anything. I have a constructive way from this recursion to see that I get high-com algebra, or more generally, so it's also true in high genera, more general homological field theory. I can just construct it really in a constructive way.
So what you said before, you had this. You studied from this class just from the commutative algebra, and then you had some special phi. And then you took the exponential of this phi and changed it due to a morphism. And that you are saying that here the one-dimensional one
Yeah, so this trivial one will be actually a direct sum of one-dimensional, so it will be semi-simple.
And then you do exactly the same. You just take as phi the what comes from the
Yes, instead of phi, I can tell you what I get. I take an inverse Laplace transform of the half of the Bergman kernel.
Okay, and you said that the x and the y were here to tell you how you bundle together these one-dimensional ones.
Yeah, actually, for y, there is an extra condition to be exactly in this thing, because in principle, when you have this kind of gadget, right? For example, you can write this generating series, and you can solve it a little bit, shifting. For example, if you have here some natural variables to control these gadgets, right? With two indices, one is corresponding to that and one to this, as we do in Grothendieck theory. So this y kind of allows to shift them by constants. So it's a bit more than just Givental group action, what you have here. So I'm cheating a little bit, but it's a kind of, so under some condition, it's always like that. There is one missing condition. But this condition is not important because otherwise you can always extend the Givental group by what I would call Manin-Zograf group. They also constructed a kind of almost trivial action on Hypercommutative algebras, deforming them by kappa classes. So so if I add this gadget also to the whole theory, then it will be the right statement. But, so in some sense, in the way we are writing it now in our paper is that we just impose an extra condition and say that this is true. Because otherwise, as I said, so you know the element of the Givental group from B. So the equation, so y has an expansion, right? So you have an infinite number of extra parameters. What to do with these parameters? So the answer is that these parameters are roughly speaking the shifts of variables, so they don't do too much, but this is something still non-trivial. I mean, and this is described in my Zograf paper for Hypercommutative algebras. Good. So now I'm precise on time.
Is there any more questions?
Just just one more. Do you have any conformal invariance for these correlation forms? Or
No. But we even don't have a parameter, right, under which it should become conformal invariant.
But sometimes in your series you get like quasi-modular forms and things like that when you compare this.
No, so I mean, at least from that end, you don't see that. So otherwise, I mean, yeah. So there's a paper of Coates and Idetani where they show how the entire group action is related to quasi-modular forms. But that's kind of, so it's a separate story.